Okay. So far, once we've gotten into electrostatics, we've talked about positive and negative charges. If I have like charges, they're going to be attracted to each other. If I have unlike charges or their unlike charges are attracted to each other, like charges are going to repel. And let's look at our Earth system here. So this is good old Earth. And remember, if I do my force due to gravity and I'm using my universal gravitation, I got mass 1, mass 2 over r squared. And if I have an object here, we know that that object is attracted to the Earth and it's going to fall down. And when we deal with this, we can look at what we call a field force. So anywhere that I'm in Earth, I'm going to have that field force is going to draw my object towards the Earth. It's actually going to draw that object towards the Earth, and we've got that taken care of. Emily, are you seeing my screen? Or are you seeing? Okay, all right, we got it. It looks like it's okay here. So you've got this field force that's coming down. Now let's look at how we've dealt with this in the past. If I go to Newton's second law, right? When we write down Newton's second law as mass times acceleration, but if we're using the universal law of gravitation, this is the mass of my object, and this is my object. And then I've got my gravitational constant, the mass of the Earth, and the radius of the Earth. And this all gives us our acceleration due to gravity. So depending on where I'm at, I get my acceleration due to gravity, and I can do this item and break it apart. Well, when we deal with a charge, a couple of things. One is my charge. If I have a positive charge, what we're going to say is we're going to draw our field going from positive to negative. So we're going to draw our field like this. And we even talked about the fact that we can talk about our strength of our field. We can increase the strength of our field by looking at these field lines. Now, the reason we draw it like this is because if I put in what we're going to call a test charge, and we assume our test charges are positive, we know that this charge is going to want to be pushed away from our positive charge. So we're going to get this idea of a field, but we're going to define our field as an electric field. And we're going to define this electric field with a big capital E. And it's going to have direction. It's going to be a vector because we know its directionality, just very much like my Earth system here. I'm going to get my directionality, and it's going to be a vector. Now, this is where things get a little interesting because we did this before, right? We've done this before. And I'm going to look at Coulomb's law. And remember, Coulomb's law is F K Q1 Q2 over R squared. Now, we're going to say that our charge, we're going to group these together just like we grouped in our Newton's gravitational one. We're going to group that together. and this is going to be my test charge. All right. So just like when I worked with gravity, we gave this a name. We're going to give this a name that we're going to work with, and we're going to define that as our electric field. This is going to be defined as our electric field. Now, when you're in your textbook, that's not how we actually do it. We actually do it this way. We actually say that E, our electric field, is going to be defined as our force divided by our test charge. So my electric field is going to give me that directionality of the force. So if I have my positive charge and my positive test charge, this is going to want to move away, but my electric field is also moving away from my positive charge. Now, what's a little different is because we're dealing with electrostatics here. If I have a negative charge, my charge is going to look more like what we're more familiar with in terms of gravity. And my test charge is going to be wanting to be drawn into my negative charge. So we get those electric fields are going to be looking just like that. So we can do a lot of things. One is if I'm given the force and I know what my charge is, I can determine what my electric field is. And my units for this are going to be in Newton coulombs. We'll also see later on that we're going to get it in a little bit different types of units, not just Newton coulombs, but we're going to get a little different units. But we're going to be able to do some things that are pretty nice because it's going to be a little easier to deal with than what we're dealing with our electric forces. And in fact, we will want to know, just like what we want to know on around where we are on Earth, what is our electric field. So we can calculate that. So if I have a charge here, we're going to give ourselves a charge, and we're going to say that this is a 12 microcoulomb charge. We want to know what the electric field is at this point. That is, R is equal to 0.5 meters away from this charge distribution. Well, that's going to make life a little easier to be able to do that, because we will be able to look at our electric field. There's our definition of our electric field. Hang on just a second. I got two computers going here. And we can do this as E, the magnitude is going to be equal to K, my charge distribution, divided by the radius squared. So in this case, my K is still 8.99 times 10 to the 9th. My charge is 12 times 10 to the minus 6. And my radius is going to be 0.5 meters squared. That is going to be my electric field. We can plug that into the calculator. And this is going to be Newton coulombs. So we can actually do those kinds of calculations pretty well. But this gives us an interesting idea. because now we can look at charge distributions a little differently. Hang on. So just like what we did with our forces, we can look at a charge here. So I've got a positive charge. We're going to go ahead and use our same 12 microcoulombs. And I'm going to go ahead and do a negative charge. And this time I'm going to do that. That's a negative 6 microcoulombs. We're going to give this a distance of, for grins and giggles, 0.75 meters. But we want to know the electric field here. We want to know the electric field there. And we're going to take this a little bit further in just a second. But what we'll do is we're going to call this point is going to be we'll just do that as a 1 meter away. So I need to know this distance. So that R is equal to the square root of 1 squared plus 0.75 squared. Oops. And this gives us a 1.25 meters. So the magnitude of my electric field due to my 12 microcoulomb charge is going to be KQ over R squared. So that's my 8.99 times 10 to the 9th. And I have my 12 times 10 to the minus 6 coulombs divided by 0.75 squared. Oops, that's not 0.75 squared. This is going to be, we're doing this point, not that point. So this is going to be 1 squared. So that is going to be a different number. So this is going to equal 107,880 Newton coulombs. The electric field at that point, due to my negative 6 charge, we're going to look at magnitude here. We're looking at magnitude. We'll deal with direction in a minute. It's going to be KQ over R squared. Going to put in my same numbers. Or put in my actual numbers. And that's going to be 1.25 meters squared. And I get 3, 4, 5, 2, 2 Newton coulombs. Now, just like what we did before, if this is a positive charge, this is going to look like it's going this direction. It's going to be attracted that direction. This one is going to be up in that direction. So I've got to do my vector addition. So I have to take into account my vector addition. So this one is actually going to be in the J direction, and it's positive. So we got that part is fairly easy to deal with. This one, however, not so much. So I've got to do my components here, and we've got to figure out that angle. So we got to figure out this angle and remember our trigonometry, right? So this is going to be the sine of the angle is going to equal the opposite over the hypotenuse. So if I'm going to do the angle, it's going to be the arc sine of my opposite, which is 0.75, and my hypotenuse is 1.25. And because we were dealing with rotational motion last time, we got to make sure our calculator is actually in degrees or radians or whichever way we want to do it. But we want to make sure that we're dealing with that okay. And I'm going to have my 0.75 divided by my 0.125, or oops, 1.25. And that says that my angle that I got for that angle, my angle is going to be equal to 36.9 degrees. So for this electric field, my electric field is going to be equal to 34522. And I want the x component. So in this case, look at my angle that I figured out. I need that to be the sine of the angle. So that's going to be the sine of the 36.9. That's in the I direction, and it's positive. I'm going to have the negative here. There's my negative. Get my negative 34522, and this will be the cosine because I'm dealing with this angle, and that's my 36.9 in the J direction. So I'll go ahead and do those calculations there. 34522 times. This gives me 2728 in the I direction minus 27,607 in the J direction. And now my resultant electric field is going to be the addition of these two. This one doesn't have any I to it, so we know that the I component is 2.728 in the I direction. And this one, 107 is bigger than that, so I know that's going to be positive. So I'm going to get my 107,880 minus my 27,607. This gives me my 8273 in the J direction. So what that's telling me is if I am looking at that electric field at this point, it's going to have our magnitude. And if I want to find the magnitude, remember how to find the magnitude. That's going to be the square root of my two components. This gives me an 82,906 Newton coulombs. So that's the magnitude of my electric field. And the angle that I would have at that point is going to be the arc tangent of my y or divided by my x. So we'll get there. We'll go ahead and do that. Running out of space on my paper. And that says it's going to be 75.5 degrees. So if I were doing this on that simulator that you guys have for your laboratory, what that is telling me, if I were to draw the arrow at this point, I'm going to have the magnitude of the arrow is going to be that 82 or 83,000 Newton coulombs, and my angle is going to be my 75.5. So if I were able to drop a charge right there, this is the direction it's going to move based on my electric field. So let's think about this for a second. Let's look at our electric field, and there's a reason why we deal with electric fields. Because what we're going to do is we're going to get charge distribution. So when you guys are doing and visualizing your electric fields on that one laboratory, we're going to go ahead and say, I've got a proton. So for every one of these positives, we've got a proton. And I've got a proton here, and I've got a proton here, and I've got a proton here, and I've got a proton there, and I've got a proton there, and I've got a proton there. And I can do this where I have a negative, a negative, a negative, a negative, a negative, a negative, and I can put this on a surface. So I'm going to put this on a surface. And this is a positively charged surface, and this is a negatively charged surface. Well, we can already infer from this what the electric field is going to look like. Because remember, I'm going to go from positive to negative. I can draw my field line. And I can do that again. And I can do that again. And I can do that again until I get to the edge. And then what's going to happen is it's going to do something that looks like this, right? It's going to give me what we refer to as edge effects. But I can actually sit here and I can draw these things to look like this, and then I can have my edge effects over here. But I want you to look at this real quick. If I do this plate here, and those are negative, and this plate here is positive, inside of here, I can get what we call a uniform electric field. I get a uniform electric field, and I can start doing something with that. And we know by experience that we can do this. So I can take a piece of aluminum foil, and I can take a piece of aluminum foil, and I can separate it by a distance, a little distance here. Okay, I can do that. And I can make this piece of aluminum foil, I can attach a positive to it, and I can attach a negative to it. And that's all well and good. And then I can put a little electron in here, or as Millikan did with his oil drop experiment. And depending upon what kind of charge I put on here, I can generate an electric field through here, and I can actually do a balancing act on a little oil drop experiment. And that's how Millikan measured the electrons, because he knew that electrons he made the assumption that electrons are quantized. And so depending on the mass of my object here, and if I know my electric field, I've just done a force balance. Okay, the force is going to equal my electric field times the charge. Oops, it's a Q, right? And that also equals mass times acceleration, which in the case of an oil drop or an oil drop is going to be related to its weight. And if I know the weight of my drop, and I know my electric field, I can calculate the charge. Right? I can calculate the charge, and then I can determine the number of charges on my oil drop. I can do this over and over again, and then ultimately I can figure out the actual charge of my electron. So that's exactly what Millikan did, and we were able to get that, and it makes a whole lot of sense, and we can look at it. But this also does something else for us. All right. This also does something else. Now we're going to describe something called flux. So we're going to get this weird concept of flux. We're going to use the mathematical symbol of flux to be that large Greek letter. And let's think about that for a second. So if I have a bunch of charges here, I got a bunch of positive charges. Let's deal with my nucleus and my proton, right? Or my nucleus of my atom, and I've got a positively charged atom. So this nucleus here gives me my charges. We can calculate the electric field based on those charges, right? We can draw our electric field because we can do that with a simulation. We can do that now. And then I can put an object in here. I can do an imaginary piece of aluminum foil. And I can count the number of lines that go through that. And that's the number of lines that give us that flux. Okay. So what we're saying here is how many lines are going to come through this imaginary surface. And we can look at that in terms of our flux. Oops, my mouse. We can look at that in terms of our flux. So let's look at that a little bit, and let's define our flux here. So let's imagine that I'm way away from my charge and I'm playing Miss Frizzle. And if I'm way away from my charge, my wavefront is going to look like that sound front, and it's going to look like I'm getting these individual lines are all going to look parallel to me. They're all going to look parallel to me. Now, the maximum number of lines that go through this is when I draw my surface such that my surface is perpendicular to my flux lines. All right. And then my flux is going to be equal to the electric field, the magnitude of my flux is going to be equal to the electric field times A, where this is the area of my surface. All right. And we've sort of seen this before. Okay. We've sort of seen this before. This is called a dot product. We can take these things together because then if I want to do the minimum number of lines in this situation, here are my lines, right? I'm going to put my surface such that it's what we call parallel. So this surface is going to be, the surface is parallel to the lines. I get my surface parallel to the lines. And then in that case, my flux is going to equal 0. My flux is equal to 0 because I'm going to deal with, this is the maximum. So I'm going to put some factor here that equals 1 when I'm at 90 degrees, and it equals 0 at 0 degrees. And we have something that does that. Cosine of 0, make sure I've got that right. Yep. Cosine of 0, you can plug it in the calculator. Oops, I did this right. Oh. I'm measuring it wrong. Not yet. My area. Because this is going to equal, but my flux definitely equals EA. This is where I'm going to be at 0 degrees, and this is where I'm at 90 degrees. That's where I got my confusion here. So that's where we get the area, because I want my cosine of my angle. And this is equal to 0 degrees, and this is equal to 90 degrees. So this is when they're parallel, that's when they're perpendicular, but it's how we're measuring our angle. And that's still going to give us this way, that gives us cosine of 0 is 1, and the cosine of 90 is 0, and we get our numbers work out. So this gives us our idea of flux. Now, this leads us to Gauss's law. And Gauss's law says, I want to write it out so that I don't make a mistake, just like I just did, that the electric flux through any closed surface is equal to the net charge inside the surface. Divided by our permittivity free space. So Gauss's law says that my flux is going to equal my net charge divided by the permittivity of free space. So think about this for a second, okay? Think about this for a second. We just talked about the fact that I have a bunch of protons here, and we can generate my electric field around here. And we looked at our flux through that surface. But what Gauss's law is telling us is if I have a charge outside of my box, the charge goes in and it goes out. And if there's no charge in here, I'm not going to have a flux through my box. I'm not going to have a flux through my box. My flux is going to be dependent, or the flux in my box is going to be dependent on what the charges are on the inside. So if I have a surface, and that surface can be any surface, I can have it be a weird surface, as long as it's a closed surface. So we think about it as a sphere. We usually deal with spheres. And I've got my charge in here, and my surface is going to be based off of that. And I get my flux is going to be based off of whatever the charge inside is going to be. So I get that charged inside. I'm going to encourage you to review a couple of examples. And this is one of the reasons why I give you the examples. I want you to look at your examples in your text on flux through a cube. And I want you to look at the example of the electric field of a charged cell. And one of the things I want you to do when you guys are doing your simulations for the lab, create yourself a charged object here. Okay, create yourself a charged object. So you can do this. You can add your little positive little protons and create yourself a closed object in your simulation. And what you're going to find is there's all my positives here. You're going to find that your electric field is going to come out and give you some weird things at the corners. But you're going to find that, guess what? There's no flux inside the closed object. So you can actually look at that, because what will happen is if my flux, and when I do this times my area, and I'm inside my electric field is going to end up being 0. So you can solve for the electric field and you can go backwards and you can come back and get it. So definitely look at that. Play with this when you are dealing with your laboratory, because that's really going to help you get there. And this also leads us to what we're going to start with tomorrow. We're going to start with looking at capacitors tomorrow, because if I do something like this, I have now created an electrical device. I have created a capacitor. Not only to do that, I have also created a nice way to get a uniform electric field, which if I were doing old X-ray tubes or television tubes or things like that, this is how we generate an electric field to get a uniform electric field. And these are easy to make. These are super easy to make. And being able to know the magnitude of my electric field is super easy to do. So we've got a lot of different things there. So we've finished this chapter now. And I'm going to do a real quick couple of summaries here. One is we deal with our like charge, our like charges are going to repel. Our unlike charges are going to attract. One of the things that we didn't talk about, but we talk about it in chemistry, is that electric charge is conserved. This is a very important idea in terms of chemistry. For those of you that are going into biomedical stuff and all of that, this idea that my electric charge is conserved allows us to understand a lot of different processes. chlorophyll, a lot of different things that happen is because this electric charge is conserved. It's what's happening to the electron and where is the electron that's allowing us to understand physiology. It allows us to understand our currents. It allows us to understand a lot of these things. So this idea that electric charge is conserved is really important. We know that the electron is a fundamental particle of the universe, and it's 1.602 times 10 to the minus 19 coulombs, and it's negative. So good old Benjamin Franklin picked wrong. We talked a little bit about conductors. Conductors are materials that are going to allow for the electrons to move, and these are generally going to be metals. And really good conductors are in the center of the periodic table. Materials that do not conduct electricity are called insulators. So we have those. We've had Coulomb's law, which is F is equal to K, Q1, Q2 over R squared. We use our superposition principle to be able to add our forces or add vectors, because we do it both for forces and for our electric fields. Our electric field is defined as our force divided by charge, or our force is going to equal the electric field times the charge. We'll use both of those in numerous places. We've looked at electric field lines and being able to see the electric fields. Now you understand why it's important to do that visualization laboratory so that you can actually look at it. Okay. Couple of things that we didn't talk about is that if I have an object like this, charge will end up being on our sharpest point here. And that'll be kind of an interesting idea, but that's why lightning rods work. That's why a variety of different other things work, that the charge is going to be highest on our sharpest point. And the charge on a conductor is always on the surface. Kind of an interesting factoid that they're always on the surface. And I don't have them inside. And then we get our electric flux is going to equal our electric field dot product with our area, which gives us our magnitude of this. And we get Gauss's law, that is EA is going to equal, for a closed surface, the charge inside divided by the permittivity of free space. So this is where things get, these ideas about flux and Gauss's law come into play. Those of you who are dealing with x-rays, looking at imaging, sonography, all of that kind of things, this idea of our flux becomes important. Our being able to generate our electric fields become important because we use that electric field in a lot of our analytical instruments. So that's where those things become very important, because typically we're not sitting out there trying to measure the force off of an individual electron. That's just not something that we're doing. But this idea of how to use and manipulate electric fields do come into play. And when you think about the body and you think about the heart, because what we're gonna see in the next chapter when we do capacitors, think about how you shock a person's heart back in, looking at doing EKGs, looking at EEGs. A lot of these things are going to come into play that we're looking at a fundamental level of where we're headed, but we'll ultimately bring it together and we'll use it in the real world. So I know brains are full because Flux always fills my brain. That's one of those ideas that you're going, okay, that makes a whole lot of sense. Not, but it